Please pontificate on the propagation of radio waves.
That way I can associate.
We've got to be able to correlate.
Am I seriously out of my red marker already?
I can get you a red marker. Actually, draw that thing a little bit higher. You want a red marker? I got you a red marker.
Thank you.
Most of the down right medium.
And Skyway. And space wave. So, radio waves have different characteristics based on the frequency at which the frequency that they have. We have three different ways we can use for radio navigation, which is pretty much the gold standard in navigation and aviation. So, based on the frequency, low, medium, high, ultra high, we can have a possibility of three different waves. We can have a ground wave, we can have a sky wave, or we can have a space wave, per the Instrument Flying Handbook under radio navigation aids. So the first wave is born of low frequencies, and because of the low frequency of the wave, it has certain characteristics of a ground wave. Well, what does that really mean to us? That means that any navigational aid using low frequency radio waves will not be subject to line of sight limitations. The radio signal simply follows the ground and goes over hills, mountains, so on and so forth. The next type of wave, which is typically your high frequency, is your sky wave. And it has some characteristics that make it a bad candidate for radio navigation aids when we're talking about site-specific aids. When we talk about the LORAN chain, it was probably a little bit more beneficial to extend the range to use a wave like this. But LORAN chain has been shut down for a couple of years now, and it was not site-specific. So pretty much HF communications are the only thing that I'm aware of as of right now that utilizes high-frequency waves. And the reason they do that is to make use of the fact that a sky wave simply bounces off the ionosphere and comes back, which makes it travel a little farther, so to speak. It extends the range, sort of like Viagra for radio waves. And then finally we have a space wave. Space wave is more like a gun. You shoot it off and it just keeps going into space. All radio navigation aids that are not NDB utilize a space wave because they use very high frequencies. So, we're going to go from front to back, back to front.
What would utilize a ground wave?
The NDB, which is the first thing we're going to talk about. NDB navigation stands for non-directional beacon, and it does exactly what it says. It puts out radio signals in all directions. Sort of like as if we threw a pebble in the middle of a nice calm pond. Those water waves would travel out in all directions. Now the question we have to ask ourselves is, how does our aircraft know where that pebble fell? You know, visually we can see where the wave hits here and the wave hits there. We can actually triangulate that, but that's really not what our system does, the ADF system in the airplane. The system in the airplane utilizes two different types of antennas, or two different kinds of antennas, a sense antenna and a loop antenna. Now, the easy way to demonstrate this to your students is to have them be an ADF and you be the NDB. So typically when I talk about this in the course, I ask them how it works, and they say, my instructor never taught me this. I said, all right, close your eyes. Now I want you to point at my voice, and I want you to keep pointing at my voice. And I'll start moving around the room, and they'll follow me with their little ADF pointer. And after I get a little bit of that done, I say, okay, my question is, how did you know where I was? So I could hear you. I said, yeah, you could hear me. You know, you have a sense antenna and a loop antenna. And through each antenna, you work out a specific direction. When melded together, you have an actual direction of where I'm at. And the ADF works the same. We must have those two different antennas because one antenna gives us good sensing in one area and the loop is a different one. You can read more about it in the Instrument Flying Handbook, but to keep things simple, that's the best way to do it. Ask them, how did they know where you were at? And then you could say, well, instead of sound waves, we use radio waves. And instead of ears, we have antennas. And that is how the ADF works. Now, the ADF itself is very, very simple. It really only comes in 4 forms. We have a fixed card ADF, we have a movable card ADF, we have a remoted card ADF where, it's like a HSI, it's slaved, and then we have an RMI. An RMI is a different instrument, it's a hybrid. It tries to make use of VOR and NDB navigation and displays information just like the ADF would. So, we know that it uses a ground wave, so it's not subject to line of sight limitations, but it is subject to a bunch of different disturbances, which you could read about in the Instrument Flying Handbook. We're going to talk about a few. We know how it works now, and it uses low frequency waves. The range we get out of an NDB will depend on how much wattage we want to throw through the transmitter. Obviously the more watts, the farther the range. And NDBs come in 4 different flavors. We have a compass locator, we have a, what's next? Medium homing, homing, and high homing. So, those have...
What homing?
different service volumes is found in AIM 118, a little table that tells you the typical service volume you'll find based on the type of transmitter it is. So first one we have is a compass locator. It's very, very, very weak. I think it's 25 watts or less, and we have a service volume of approximately 15 nautical miles. Now, that's important for us to understand because when we use a compass locator, it's in conjunction with an ILS, and it's really more like a poor man's GPS. Back in the day, without that little screen and the magenta line to follow, we really almost had no idea what was going on except for that they were giving us vectors. Our situational awareness was a little bit easier and harder to compute. So we had a compass locator that basically told us whether we were right of the course or left of the course when we're outside of the service volume which the ILS provides. So we could tell when we're in a downwind vector whether we're on the north side of the field or the south side of the field. We can even navigate to the NDB and then fly the course outbound, do a procedure, and come back in. So the NDB was over there was really, really handy. They call it a compass locator, except for when it's co-located with an outer marker, they call it a locator outer marker. And the compass locator can be used to substitute the outer marker if it is broken. So part of the marker beacon system, which we'll talk about later, this thing's very important. Next, we have a medium homing NDB. Medium homing NDBs are actually kind of easy to spot because A, they're not on the ILS path, and B, they don't utilize any low-frequency airways. So when we look at the chart, we know that Fort Pierce has an NDB on the field, Fort Pierce NDB, but there are no airways that go to it. We use it just pretty much for approaches and to provide for a feeder route to get us to Zaza. When you look at the chart, you'll see there's no low-frequency airways going to it. Ergo, it's a medium homing NDB. Now, we can double-check this if we simply go to the ADF. And the ADF, under Radio Aids And Navigation, it'll say Fort Pierce NDB.
You mean the AFD?
HW, yes, the AFD.
Okay.
What did I say?
ADF.
Oh, sorry, AFD. Airport Facility Directory. So we go to the Radio Aids And Navigation part underneath it all, and it lists all the radio aids and navigation in the local area. We can find out what type of VOR Treasure is. We can find out the compass locator Lucy, which is deactivated. We can find out what type of NDB that Fort Pierce is. It happens to say it's an MHW, a medium homing without voice. For more information on the W, you can see the actual legend in the first few pages of the AFD. So, next we got our homing and our high homing, and they have different service volumes, and these do make up the NDB airway system. Their job is to provide for long navigation. This guy's more like a terminal VOR. This is even less like a terminal VOR. And these guys are more like VOR low and high, so to speak.
What point is that? Is it under Fort Pierce in the AFD?
Yes. So check under Fort Pierce in the AFD, you will find it.
Pierce NDV.
Yeah. Without.
Now, we can back that information up on an actual low and root chart just by looking at the frequency for the NDV. It is underlined, which means there's no voice over that. So, but that's what the W means. You can look it up in the beginning. There's a little legend to use. So, 4 different types of NDVs. We now know how they work, what kind of service volumes they're dealing with, and the reason for them. ILS, terminal, low and high, so to speak. So,
Darth Vader breathing. Better not come over to my house. Bring a beer with you.
today's discussion is going to utilize a fixed card ADF and a simple formula if we don't have the ability to figure out angular differences and being able to visualize with our heading indicator. So what I've drawn is an NDB with the 180 bearing. Very important we understand this thing does not put out radials, it puts out bearings, so says the FAA. So we have 3 different aircraft, aircraft A, aircraft B, and aircraft C. We're going to try and figure out visually and mathematically what our relative bearing really is. Simple enough. So, aircraft A is going 30 degrees, and we want to figure out what this ADF should read when it's on the 180 bearing. This type of practice is very important because when we do NDB approaches, procedure turn outbound, we're good, but procedure turn inbound, we have to recognize a 45-degree angular difference between our ADF. So this is really where we're sharpening those skills. Now, all the aircraft here pretty much have movable card ADFs, but in the off chance that you don't have one or you want to train your students to be able to use a fixed card, simply set north, nose, up top. So, first, let's try and figure out visually what it should read. Now, here this aircraft is going 30 degrees. Imagine if I take and put it right there on the 180 heading north. Where would the needle point?
North.
North. But it's not going north, is it? We're going to shift it this way by 30 degrees. Well, if we shift the nose 30 degrees that way, where's the needle to the ADF supposed to go?
330.
Yeah, it's supposed to go 30 degrees to the left. There is an angular difference here between north and 30 of 30 degrees. So instead of being like this, we have to shift it 30 degrees the opposite way. So it should read 330. Now, let's see if we can work this out mathematically, just to sort of ensure that we got the right answer. We know what our magnetic heading is. It's 30. Actually, I'll look it up here. What we're looking for is relative bearing. We already know it to be 330, but, we'll just pretend we don't know what it is. Now we need to know what our magnetic bearing is.
Wasn't the needle supposed to point towards the station?
Yes. When this aircraft flies over here and is now on the radio, it's still pointing to the station.
Sure. But since
you're going 30 and the station's actually due north. So it should point 30 degrees left. Telling you, hey, that NDB isn't in front of you, it's 30 degrees left.
Okay. So you're assuming once we're on that 180 bearing to the station.
Correct. Now, in our current position, no, that's not what it would read, but what I was getting at is when we get over this 8 bearing, what should it read on our fixed card? So, we don't know what our relative bearing is, but we do know what our magnetic bearing is. What is our magnetic bearing?
180.
Magnetic bearing is always to the station, not from the station. So, we have to put 360. When we're on the 180 from, we got to be 362. That's our magnetic bearing. Remember, magnetic bearings always take us to the station. Relative bearing is on this thing, and we know what magnetic heading is. So now it just becomes simple math. We got to get rid of this guy to get RB all by himself, and we get 330. The same thing we just visualized, but mathematically we've double-checked it, and it is correct. So this is simple. I don't even know if you'd call it algebra. Maybe you do. I don't know. So we know that aircraft A, with a fixed card compass, can be able to tell that he's on the 180 bearing from this NDB when the needle points to 330. So how we would actually use that when it's about 335 or just below, then we make a turn 30 degrees left and intercept that bearing, the north, the 180 bearing from, and fly north to the station. Once we turned inbound, the needle would go up to the north, and then we'd use simple ADF tracking techniques as outlined by the Instrument Flying Handbook. For wind correction, let's say the wind blows us over by 5 degrees. We have to figure that out, double it so we go 10 degrees to the right, and then when we had a 10-degree disparity between what our nose is doing and what the needle is, then we turn 5 degrees left and continue to track to the station with the proper wind correction angle in there. So that's aircraft A. Let's give you something a little bit more complex here. Aircraft B. Aircraft B is heading 270 degrees. How will this aircraft be able to tell when he is on the 180 bearing?
090.
Simple enough. It's got to point this way. Time for the mathematical double check. Our magnetic heading is 270 plus relative bearing equals, and we got 360. Minus 270, minus 270. So our relative bearing is 90 degrees. So when that needle points to 90 degrees, we know for sure that we are in fact due south of the station. We can either turn north and go to the station, or we can turn outbound and track outbound as if we were on NDB approach. And finally, for the toughie, as if they're all tough, aircraft C. He's going 240 degrees. What should that needle point at to let him know that?
120.
Let's do the math on that. See, I'm a visual guy. I can literally just, if we're going 270, it should be pointing 90. We shift the nose this way, the needle's got to go the opposite way. We've done it by 30 degrees in this case, 30 degrees. That's how I do it. But for people that love their math, it's also pretty easy to do. Yep, 120. So, mathematically speaking, we can always figure out what our relative bearing is, if we so need to. But really what we use these formulas for is to figure out what the heck our magnetic bearing is for. That's how we really use them. And we use the same formula. Right now, when we're over here, we can figure it out reverse. Let's say we're here going 240. We would then say, well, what is the magnetic heading we would have to fly to get to the station? Now, here we know this reads 120, so you can make a 120-degree turn to the right, and actually, 120-degree turn to the right, and it'll get you going to the station, but some people need an endpoint so they can turn to it. So we can use that very same formula, magnetic heading plus relative bearing equals magnetic bearing, except for now we'll say we can't figure out what our magnetic bearing is. So we have to take our magnetic heading plus our relative bearing to equal our magnetic bearing. So in this case, 240 plus 120 is
360.
So we would have to turn to the north and fly to the station. So the math works either way, whether we're trying to figure out what our relative bearing is or should be when we're on something, or What's our magnetic heading got to be to go to the station? You were about to say something?
Relative bearing is kind of like what radio you're on.
The relative bearing is from you, and north being your nose, always.
So magnetic bearing and relative bearing are reciprocals?
Different. Well, no, magnetic bearing is the magnetic heading you've got to take to get to that damn station. Relative bearing is when we're using a fixed card ADF. Remember when they first came up with the system, they weren't smart enough to put a little knob in there. And so under the relative bearing concept, you are the station and your nose is always north. So N equals nose. And so when we talk about this would be 12 o'clock, 3 o'clock, 9 o'clock, 6 o'clock, only we do it with a compass instead. You know, everyone's familiar with the clock method for calling out traffic. Well, this works the same way, only instead of 12, we talk 360 or north. Instead of 3, we say it's 90 or east. Instead of 6 o'clock, we say south. Instead of 9 o'clock, we say west. So it's kind of the same concept. So relative bearing is quite simply where this thing is in relationship to you, just like we talk about traffic, and where is that traffic in relationship to you. We know that 12 o'clock is supposed to be at the nose. Again, that doesn't take into fact track, which you can read about in the AIM, but you know, in a no-win condition, that's how it reads. So when we talk about the actual relative bearing, it's relative to your position, like where is this thing relative to you. And relative position is something different than magnetic bearing, or relative bearing is different than magnetic bearing, because magnetic bearing takes you to the station magnetically. Relative is measured off of a standard datum plane, you could say, or the concept of where 360.
Can you say relative bearing is kind of like from the station?
Well, relative bearing is from where it is from you, where you are. Like,
yeah.
It's from you.
I don't know. I never did anything with this.
So, it happens.
Is it an NDB approach, man?
Nothing.
You got a good instruction.
So, when we talk about the actual relative bearing, it's relative to you, where you are the station. So, when you get a traffic call out, that's like a relative bearing, but it's a relative time. You know, the relative time position will be 2 o'clock. Well, you know, you got to look over there at 2 o'clock. So, if we did the same thing over here with the station, we would call it, well, 2 o'clock would probably be over here. Here's our NDB. They say, hey, what your ADF is really telling you is, hey, you have NDB 2 o'clock. But it's really giving it not in terms of an actual timepiece, but in terms of the magnetic compass. So,
got it.
So that's your relative bearing, just like traffic. So the best way to go about teaching this is keep it simple and talk about how to intercept and get to a bearing, which you can read about in the Instrument Flying Handbook. That's how most of the examiners want it done. You know, when they get a little bit more experience under their belt, they can skip the turn 2 and then figure out what the bearing is. They can just take a look and say, oh, look, I got an error of 40 degrees. Let me go, 90 degrees or 80 degrees that way to intercept. So, but practically speaking, when we can figure out the angular difference, we put ourselves in a prime position, not even to have to really know how this stuff works, just to understand that, hey, when we fly outbound and turn this way 45 degrees, make our 180 degree turn, there's got to be a 45 degree difference on our ADF from where our nose position is. It tells us, hey, we're on this bearing and we need to turn in. So we need to be able to recognize that. So that's more of the practical application as it relates to an airplane who's actually flying an ADF approach, or an NDB approach. Next on deck is a VOR, which stands for Very High Frequency Omnidirectional Range. Now, the NDB is the only navigational aid that uses a ground wave. All others are space waves, and I mean all others. So it's really easy if you can remember. ADF, which is the oldest, is the most simplest and uses ground wave. Everything else,
space wave.
Uses a space wave. Man, you're just messing up my bottle. So, first question I have is, how does a VOR work? And I believe the old Instrument Flying Handbook actually kind of gave a good example of it, but the new Instrument Flying, not the newest one, but I'm talking 2 editions ago, it told you exactly how it works.
It's like the spokes on a wheel.
It works like that.
This is
Sort of. It is. So let's simplify it so that our students can really, really understand how this system really works. We're going to talk about a lighthouse. Everyone knows what a lighthouse is, right?
Yeah.
You know, it's got a big, tall building, and there's a light that's a directional, and it goes round and round and round. Well, if you ever stop to look at a lighthouse closely, you'll see that at the top of that lighthouse, when that directional light reaches a certain position, the omnidirectional light on top flashes in every direction. Well, the secret to that is that the on-top light flashes only when the directional light is north. So just by looking at which way that light is pointing when the omnidirectional light goes off, mariners could figure out where north was, you know, if their compass was broken. But that's not how they use it. Believe it or not, the lighthouse is aid to navigation. It's a maritime aid to navigation. And as you know, we have certain terms, starboard, port, and nautical, that are shared in common. So we've kind of borrowed from their technology a little bit and updated it for our needs. Obviously, if we use lighthouses for navigation, we wouldn't be able to navigate very far during the day and when we're in the clouds. We'd have to change that light energy into radio energy. So, how the mariner uses a lighthouse is, first of all, he's got to know the period. You know, the time it takes that directional light to go from 360 all the way back to 360. Once he knows that, all he has to do is take a quick time difference measurement and calculation to figure out where he's at. So let's say, here's our lighthouse. We're going to give it a funky roof there. And we're going to call this north, east, south, south, west. Too early in the morning. So, here we have this funky roof's DOR. We have a little directional light there, or omnidirectional light. And all this lighthouse does is it turns in this direction. And this is my beam of light. That's all it does. However, when it gets here, the omnidirectional light flashes in all directions. So I have a directional and an omnidirectional. Now, as long as we knew what the period was, we could figure out what bearing we're at, and I'll show you exactly how to do that. Let's say, to keep things simple, KISS, that this lighthouse has a period of 1 revolution per minute. So that means it takes a full-on minute to come back to north. So, let's say we receive the omnidirectional light, and then 15 seconds later, we receive the directional light. We can calculate where we are in relationship to that aid to navigation based on time. We know that it takes 60 seconds to go a full 360. If it took us 15 seconds between the omnidirectional light and the directional light, we would have to be 1/4 of the way east. If it took 30 seconds between the omnidirectional light and the directional light, that's half a minute or 180 degrees. And if it took 45 seconds, we would have to be west. So it's a simple time calculation more than anything else. All we have to know is how fast the directional signal is moving and the difference between the directional signal and the omnidirectional signal, and we can tell what bearing we're at. Our VOR system knows always what bearing we're on, but it doesn't display that information unless we're looking at an RMI. All it does is tell us where we are in relationship to the course that we've selected.
How does the equipment interpret that?
In the same manner. The equipment knows what radial you're on. It has to. But it takes a look at what you've selected on the OBS and says, well, let's say you've selected 090, and it knows you're here. Well, it's going to tell you that, hey, your course is to the left.
Well, I understand that, but how does it pick up the radio signals? What type of calculation does it make?
Well, it's a simple system that, doesn't use much of a computer, but it is a little box with a computer in there, and it knows what the frequency is. Well, not the frequency, the period. All VORs have a standard period.
So it makes the same kind of measurement. It has an omnidirectional signal that it receives, and it compares that to the directional signal that it receives.
Correct.
So, in other words, the directional signal, the spokes on a wheel concept is not exactly true.
Not exactly
because they're not
true.
always spitting out specific radials. It's a sweeping.
Exactly. And if you were to actually read about it, the EASA stuff I gave you on your discs, they go through that. I mean, they literally, they have like a metal sleeve with an opening, and it turns at X amount of revolutions, and that blocks the rest of the radio waves and just sends out the directional one. So, TACAN works very similar, but a little differently. So, the VOR always knows where we are in relationship, or what radio we're on, because now we're talking about VORs, we talk about radials, but it doesn't tell us that readily. Its job, it's been designed by the engineers to tell us where we are in relationship to our selected course, not where we are in relation to the VOR. Now we can make it do that simply by centering the needle with a 2 indication. Now we can tell how to get to the station. If we look at the bottom end of that, we know which direction we are from it, but it doesn't readily display that at all times. If it was an RMI, it would, because it would act more like an ABF. So, how are we going to teach this to our students? We're going to do it quite simply. First things first, we got to break it down to simple concepts. That's our job. KISS, keep it simple. So there's 2 indications or 2 indicators on this instrument. I'll draw a little OBS there. We have a CDI, a course deflection indicator, and we have an ambiguity indicator, which is your to from. So, once we've selected a course, this instrument's just simply going to tell us, based on the line of position that we're going to draw, whether we're right or left of course or on course, based on what the CDI does. So in this case, we've selected 360 bearing. And we have to draw a line of position north to south. That's what the CDI is now going to tell us. Where are we in relationship to this line of position? So, here we go. This is telling us, hey, the course that we've selected is actually off to our left a little bit.
Well, depending on whether we have a to from flag.
Correct. Well, no, it won't. That'll tell us which side of the VOR we're on. We're just breaking it down to the CDI indication first.
Okay.
So, when we dialed in the 360, we have a line of position north to south right over it. So we're just talking about this indication. We'll get to the to from. So all this is telling us is, hey, our line of position is to the left. Doesn't matter whether we're in this segment or this segment, the line is still to the left, saying, hey, your course is to the left. Get over to the left. So we could, in theory, be here, 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 here. We just know we're somehow right of course, and we need to correct back to the left. Here's where the magic of the ambiguity comes into play. We're either going to get a to or from, it'll say to or from, or we'll get a fancy little needle like so. That's to. This will be from, just like that. Now, we have to understand, I don't know what that says.
That's just a reminder.
Okay. We have to understand, all right, just as with NDBs, VORs have different categories and classes, or different kinds of classes. We can have a TACAN, which is military use. You got to have TACAN equipment to use it. You simply put in the channel, and you can use the TACAN much the way we use a VOR. We have a VORTAC, which is a combination of co-located VOR and TACAN station. And what we get from the TACAN station is DME, which is our next topic. We can have just a straight VOR, like Cecil VOR, or we can have a VOR DME, like we do in Melbourne. So, those are the different kinds. Now we have different classes. We have a terminal class, we have a low class and a high class. The terminal class is really just like the medium homing ADF. It's designed to get you into the terminal area, and it's used as a navigational aid for instrument approaches. It's not part of the Victor Airway system, and it's pretty easy to see why. A terminal VOR only goes up to 12,000 feet and only goes out 25 miles. Meanwhile, Victor Airway goes from 1,200 all the way up to 17,999. You can't possibly have a navigational aid that only goes up to 12,000 support an airway structure that goes all the way up to 17,000.
Well, can they pick the signal up at 1,000 feet?
Mm-hmm.
Okay.
So there is that little bubble there, so 1,000 to blah, 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 12,000. But you can't have the terminal VOR used as Victor Airway Navigation, navigational aid for Victor Airway Navigation, because you can't get it at all altitudes that the airway actually exists on. So they only use this to bring us into the airport and do approaches on. Next we have our low, and that goes from 1,000 all the way up to 18,000. It goes out 40 miles. There is a little bit of bubble underneath that. So when we're lower, if we're closer, we can still get the signal, but that's not always the case. And this is one of the two nav aids that we use as the backbone for the Victor Airway and jet route system. The next is the high, and this is a multi-stage VOR with service volumes that are quite easy to remember if you can do it. So we're going to start from the bottom and work our way up to the top. Everyone knows it goes from 1,000 to 14,500. And that's 40 miles out. From 14,500 to 18,100 miles out. From 18,000 to 45,000, 130 miles out. And from 45,000 to 60,000, it goes back to 100 miles. So it's important to know the service volumes of our nav aids, because we expect good signal while we're in the service volumes of the nav aids. And the FAA guarantees a signal when we're within the nav aids. However, when we're outside the nav aid service volume, we're not guaranteed good or accurate signal. So having knowledge of this is very important. When we put it in scenario terms, we can ask our students, if we're flying around at 15,000 feet and we want to go off route, VOR to VOR and between two highs, how far can they be apart for us to remain within the service volumes? It's a question right out of the written test, really.
200 nautical miles.
There you go. What if we're between a low and a high at 7,000?
80.
Yeah, doesn't matter whether it's low or high.
Yeah, that's the bottom limit of the...
So, now this is important because the FAA actually goes and checks all instrument procedures, Victor Airways, NDB, low frequency airways, every 6 years. They do it all instrument approaches, everything. One thing they don't do is random off-route routes. There's just too many of them. So the FAA has a whole fleet of King Air 350s and pilots they pay good money to, and they literally fly across this country and check the instrument system.
Go to usajobs.gov. They actually have postings for them.
So their job is to fly IFR everywhere they go. So they're going to handle the eastern side of the United States in the first 2 years, the middle side of the United States in the second 2 years, and the west coast in the next 2 years. With some exceptions, when we accidentally report a nav aid broken, because we're not within the service volume, we don't know what the service volume is, they're going to shut it down, have someone come out and tinker with it, say, yep, it's good to go, and they'll dispatch that King Air to come fly that nav aid, and it hunts for the signals of that nav aid and finds out if it's working correctly, if we're getting adequate reception and signal quality and strength. So those are our VORs. We've talked about how to use them, how they work, the different classes of, what kind of wave they use. Now let's talk about some errors we have associated with both ADF and VORs. They're subject to multiple interferences.
Question for you real quick. We're flying in between two VORs on a Victor Airway.
It's been checked. You have adequate signal.
Okay.
So I said every Victor Airway, all instrument approaches, every jet route.
Yeah.
So there's a lot of things that can cause these systems to read erroneously. The most sneaky of them all is propeller RPM. It actually happened to me one time as a student pilot. Certain RPM can cause a scalloping of the CDI needle or the ADF, and it causes just a little bit of interference. It's certain RPMs that do this, so if you have a problem with scalloping where the needle goes left or right or the ADF is just kind of hunting there, change your RPM and see if that's the problem. If it's not the problem, then you might have bad equipment or some other interference. P-static is also a problem and can cause interference. P-static is precipitation static. So when we're flying around and we don't have static wicks on our aircraft, or they're broken and the actual grounding wires aren't connected between our control surfaces, we could have scalloping of the needles as well. Next is lightning. Lightning affects the VOR, but more so the ADF. They call the ADF the poor man's strike finder because it's notorious for pointing out where the lightning is. You have eyes, you know where the lightning is, but unfortunately it's subject to electrical disturbances which cause it to point anywhere but where you need to go. And with the ADF, we also have that coastal deviation. They have a name for it, coastal attenuation. Basically, as radio waves travel through the air, the different densities between over water and on land actually change direction of the ADF. So sometimes when we're using ADF or NDB for navigation along the coast, we'll have a little bit of an error there. And I'm sure there's a couple more that I can't remember, but you can read about them in the Instrument Flying Handbook. Now, both of these Nav Aid systems put out a Morse code to help you identify it. One of these systems has a flag, which means we don't have to identify it all the time, and that's the VOR. The VOR puts out Morse code. And, we need to make sure our students, for sure, are visually identifying this thing. I just did a state check-in when someone kept on hitting the DME to identify the VOR. Looking, huh? It's the DME again.
Well, you can do that Morse code about once every 30 seconds. Does that mean it's working?
So, the DME, you mean?
No, if you listen to the VOR of the DME, if you listen to the
identifier
code,
on the
same
DME.
thing. Yeah, it'd be 30 seconds. So it's working. Not necessarily. Like the DME goes about every 30 seconds.
Yeah.
About every 3 times with the...
It's higher pitched.
It's a bit higher pitch.
Did we do a little thing on DME before?
Oh, yeah.
Remember that?
Yeah.
So,
DME, man, that was back when we were young. When we first got started on this.
So anyway, we have to visually identify it, not just listen for the sound.
Maybe it's friggin' test code.
It could be a test code, TEST. Again, I don't know why they do that, because it could confuse aviators, I would just take it off the...
And again, I don't know why they don't have a audible thing that says, "Oh, the Treasure Coast VOR is functioning properly. Have a nice day."
At some stations, they do.
Why don't they do it at all of them?
Well, who's going to pay for it? Right now, we're in massive budget cuts already.
I mean, can it really be that hard?
Yeah.
Instead of a beep, beep, beep sound, to have a recorded thing? I mean, I don't know.
The recording takes longer, and, I'm sure the government contractors are going to charge an extra $15,000 just to come out and look at it if it's got voice on it.
Sure, that's true.
We got the friggin' Turpentine Springs Terminal, TST. Identify that bitch. It's on test code. It's working just fine.
Turpentine Springs.
So anyway, the ADF we have to constantly listen to if we're going to use it for navigation because there are no flags, and the needle has to point somewhere.
So moral of the story is don't use an ADF.
No, the moral of the story is listen to the code. That ADF needle will point somewhere, whether it's on or off. It's pointing somewhere. We don't want to mistake where it's pointing for where we actually want to go. So we got to listen to it, make sure that it is in fact always working because there's no flag. So that kind of covers some of the errors with both these types of navigation systems. And we talked about the different types of VORs and the different classes. Let's move on to DME.
Like a Mexican. Look at that.
Damn.
Look at that aspect ratio, man.
There we go. Here we got our Lucius, and it has DME equipment on board.
Of course, that's the one with the cowboy hat canopy extender. A cowboy hat canopy extender, so you can wear your cowboy hat inside there and not hit the ceiling.
Just for Scott. So, basically, this is a very simple system. They're all very simple systems. They use differential navigational signals or timing signals of some sort. This one uses timing signals. It starts a conversation with this guy. And a simple way to demonstrate that when they tell when you say, well, how does this system work? They say, oh, well, this sends out signals, and then our airplane responds to those signals. You take your radio signal, you throw it at them, and you target them. You're about 5 feet from me. What good did that do you? So you got to start the conversation in the airplane, send the signal to the DME station, which is nothing more than a transponder. It will respond. Your box simply gets that time and says, okay, well, it took me 3 seconds to get that signal. I know that radio waves travel at X amount or many miles per minute or miles per hour. Ergo, this is how far I am from the station. It gives a slant range distance, not horizontal distance. And in some cases, vertical distance, but only when we're over the VOR. So if we chose to fly over this VOR at 12,000 feet, the DME will read to DME. Is there any condition in which you want to read 0 on your DME?
No. Yeah, that sun goes right underneath the runway you land.
That's when Bitchin' Betty says, pull up, pull up. So basically it gives us slant range distance. We can use either trigonometry or Pythagorean theorem to figure out actually how far we are from the station. But at the end of the day, we're not that concerned with it. We can get ground speed readings, we can get miles per hour, miles per kilometers per hour, and we can get distance from the damn thing. It's a handy old-time system to give you situational awareness when you're on a Victor airway.
The lower and longer range we are,
the more accurate we're
more
going to be
accurate that slant range distance will have to do with our actual distance.
It's 1,000 feet vertically per nautical mile horizontal. Is that right?
That's what they say. Okay, down here.
It's like a 1-to-6 ratio.
Down here, we're going to be most accurate. We are, in fact, 2 miles from the station. Up here, we're still 2 miles from the station, except we're actually over it. So when we talk about the horizontal distance, the DME reading will be most accurate far and low, and least accurate high and low.
Okay.
So, DME is just simply a tool that helps us gain a little bit of situational awareness when we're tracking VORs. We're flying long distances with the needle centered if we're good. If not, it's over here to the left for some time, and it's over there to the right. So it kind of tells us where we are in between VORs. Any questions on that?
Nah.
Now, what was the
max range is 199 nautical miles, and I think you can have a max of about 100 or so people using it at any time. Because remember, this is a transponder. It only has so much time in between signals where it can reply to other people. So basically, it's going to pick the strongest signals and provide them information, and the weaker signals is going to say, "Oh, you're too far away. Get out of my way." So not many people have this system anymore. So guess what? It's really not a problem anymore. So moving on to GPS navigation. What type of wave does the GPS use?
Hold on. Is there any kind of a DME other than a localizer DME that's not incorporated with a VOR? Is it just a straight up DME?
Yeah, you can have an LDA or an SDF.
Yeah, but it's not has to do anything with the approach. You can just have a DME on
the
field.
DME on. It's not a standalone DME, but you can have a DME co-located with an NDB, for example. If you look at the lone route chart, it'll tell you, hey, all these different nav aids can have NDB.
But it will always be co-located with some kind of navigation aid.
There's no reason to simply put a DME transmitter out in the middle of nowhere. You gain nothing by it, but you pay all the costs for it. So there has to be a good reason.
You want direction and distance at the same time.
So on the GPS. Now we got to think outside the box here to really understand it. And you can ask Mr. Bosquero about it. Because he didn't do so well on this even though we went over it.
0.3, man. It gets everybody.
So, well, no, it wasn't that. We're talking about in the world.
Oh.
The GPS needs a certain amount of satellites to give us a 3D position in space. How many satellites is that? 4. We have 1. Think about a basketball. We could be anywhere on the outside of that basketball. We take 2 basketballs and meld them together. We can be anywhere around that ring. You take a 3rd one and put it in there. Now we got 2 points. We need a 4th one to figure it out. So we need 4 satellites in view simply to tell us our 3D position in space. That's that long in altitude. But we always hear talk about 5 satellites, 5 satellites, 5 satellites. What does that 5th satellite do?
Receiver autonomous integrity monitoring.
When we check rain, the only thing we're checking is how many satellites we're supposed to have in view during the time of the approach. That's all we're checking. We're not checking the box or anything like that. So if we have 2 GPSs, there's no need to look at rain twice.
Not the VOR, no reason to ident both VOR.
Exactly. Really, no good practical reason other than we have absolutely nothing to do better, and we'll just do that. So, this is how rain really works. We got satellite 1, 2, 3, 4, so we can get 3D navigation. We got satellite 5, which means now we have rain or the ability to utilize rain. So, how does that work? Well, remember, we only need 4 to calculate our 3D position. How many we got?
4.
That's all we're doing with rain. We're stopping listening to one satellite momentarily and we're replacing it with this one. So when we get solutions for satellites 1, 2, and 4, the same in satellite 3, when we replace that satellite 3, we get a different one. We can say, hey, that satellite's not giving us good information. Now, what might cause it to give it bad information? Well, maybe it's broken, or maybe it's just subject to a little bit more atmospheric disturbance. And so we use something called FDE, fault detection and exclusion, to stop listening. We're no longer interested in what it has to say. Sort of like that cheating girlfriend. Oh, baby, I won't do it again, I won't do it again, I promise. Hey, get out of here. So we're done listening to it. Do we have rain anymore? No, we do not. So, used to be back in the old days, we had 24 satellites with 3 spares, so that's 27. Depending on which book you read, that's going to change. We have over 30 now in there in the constellation. And there's the control over in Colorado Springs or Steamboat Springs, Colorado. That's kind of the main nerve center there. They control all the GPSs. And basically it's just a constellation or a system of satellites that orbit the Earth in certain planes, and we're able to look at them. And what the satellite really does is each one has its atomic clock, and it's all set to be very precise and accurate. And it sends us a signal. And that signal is time-stamped with the atomic time that it sent the signal. So we take in our box and we say, okay, well, it took us 50 seconds to get that signal. We must be 17,000 miles from that particular satellite. And we do that with all of them. So it works a little differently than DME, because DME we need a response. We need to call out and hear a response to figure out how far we are. This one, we don't have to, respond back to the satellite. The satellite says, I called you at 10:15. You get the call at 10:16, okay, well, I got the call at 10:16, that was a minute. I'm 17,000 miles away from that satellite. You do that with all these. So, this system was kind of the beginning system, but it's not the greatest way to do things. Remember, rain can go out at any time, whether we calculate it or not. And when we talk about rain, rain stands for Receiver Autonomous Integrity Monitoring. Receiver, what's in your airplane? Autonomous, automatically always does it. Integrity monitoring. So that goddamn box is always checking rain. Why we have to check for it on approach is the dumbest fucking thing I've ever heard of. Because if you don't have rain, it's not going to arm to approach. You won't see APR in there, which automatically tells you, oh, I can't.
So if you don't actually go through its sequence and check rain, the receiver will do it itself before it switches to approach.
It's always doing it.
It's always doing it.
Autonomously.
So it's kind of silly, but that's the way the FAA says, so we listen to whatever it is they're saying.
So if you don't check it, it'll still come up, it'll say rain unavailable or whatever.
It'll say in the 430s in the bottom left corner of the box where we usually see APR, it will say INTEG, meaning, hey, you have a problem with your integrity, and it'll be in yellow. So it automatically warns you, but, we got to make things difficult and complicated sometimes, so we got to check rain before we do this. Now that rain check is only valid for 15 before to 15 after your intended arrival. So what that rain check really does is just, it checks the database to ensure that we're supposed to have 5 satellites in view over that time period. That's all we're checking. We're not checking the receiver. We're just checking the database to see, hey, will we be having any outages where we have less than 5 satellites in this general area, which is usually your missed approach point for this time period?
You usually have 6, 7, or 8 satellites at a time, don't you?
Or more. When you get to Q1000, you can see 10. So that's because we have more than 24 now. We have 30 plus, and then spares. So rain usually isn't a problem these days. But rain is old news. RAIN uses its TCO 129 equipment that was kind of like not VFR GPS, but it was the infancy of GPS navigation. We got that new thing called WAS. Now what WAS does, something special that means we don't have to mess around with RAIM any longer. What WAS does is actually very special, very easy, and pretty sweet. We got a master WAS satellite there. So basically, we have ground stations which are listening to the satellites. And it knows exactly where that satellite should be. And it takes a look at the difference. Remember, as it passes through the ionosphere, that radio wave kind of gets shifted a little bit, much like when we look down in water. So the timing signal gets distorted a little bit. So it takes a look at that satellite, it takes a look at this satellite, and vice versa. It knows where the satellite should be versus where the satellite says it is through these timing calculations. And it sends all that information right there to the master station. So the master station takes a look at the information like a supercomputer and says, okay, well, how are we going to correct for this? It says it's 17,120 nautical miles, and it's really supposed to be 17,119 and a half. We've got to send a correction signal there. So then, this guy talks with one of 3 geostationary satellites over the United States. Again, depends where you read, but if you at least Wikipedia, they talk of 3 different WAS stations that control these geostationary satellites. I know for the fact there's one on the East Coast and there's one on the West Coast, because when it went down, Alaska lost some of its WAS coverage. They fixed it and got it back in the service, but it did go down. So there's at least 2, but probably 3 geostationary satellites. That means it's in a geosynchronous orbit. It stays precisely over the location. It rotates with Earth. And so what it does is it sends correction signals to our little Jetsons airplane here. So that we correct the satellites that we're looking at. So we get a hyper-accurate navigation solution, not subject to RAIM or any of that nonsense. If you're flying WAS equipment, the whole world opens up to you for IFR. TCO 146 equipment does not need any other equipment installed on board. All you need is a WAS receiver and a GPS unit. That's all you need to fly IFR. There is no RAIM issues with it. When we file for alternates, we don't have to worry about if our alternate has GPS-only approaches because we have WAS equipment. And WAS is not subject to any loss of satellite. Doesn't matter if we lose that 5th satellite. We're guaranteed to have forward any time.
Yeah, but if you lose a geostationary one, like you said happened in Alaska, you could be in some trouble.
Then you would be in some trouble.
But you don't have to have a ground-based navigational aid for
WAS equipment.
For your WAS equipment?
No.
No GPS you do, if you're going to do that as your alternate,
You would probably
right?
be able to still reach the other satellite, because the satellite doesn't just handle this sector. You can probably still talk to the satellite next to it and get navigational signals, but when you're up in bumfuck Alaska, you're just so damn far away from the geostationary satellite that you'll lose that service. You won't be able to get the next one over. But that's why it isn't subject to having to check RAIM all the time, because it doesn't use RAIM. It uses this method that I've taught you to check to see whether we're getting good signal or bad. We don't need to take that bad signal and stop listening to the satellite. We just correct the signal. So it's a different way to go about doing the same thing more than anything else.
Okay.
Now, as you would guess, these use space waves, and they are line of sight where that can come into play is when we're flying around in the canyons and the mountains. We might not be able to see certain satellites depending on how low we are, but it's usually not a problem because all the satellites are up in the sky. So unless we're going to be flying through tunnels, we don't have any problems with that. Any questions on it?
Nah.
Finally, we got the ILS system, the instrument landing system. It's made up of 3 different components. We have the guidance component, we have the range component, and we have the visual component. The guidance component is provided for by the glide slope and the localizer. The range component is provided for by the marker beacon system or DME, and if we need to, we can actually substitute the locator outer marker, the compass locator, for the outer marker. And the visual is simply your runway lights, the touchdown zone lights, or your approach lighting system. So those are the three possible components.
Happy or Gazzy's not considered part of
So they're considered part of the runway environment, but they're not part of an ILS installation. So those are the three components we could have on an ILS. It's important for us to understand that out there, beyond the Delta airspace, they have things called ILSs that don't have DME associated with them. So we can't always put IFJD or ITIX or I anything in there. And back there, out there in the real world, we might have to identify things with cross radials. You know, that's a very big problem I see here. When we teach people to fly these instrument approaches, we teach them one way to fly this approach, when you really don't need to do that. First of all, you don't even need DME on ILS, but everyone types in IFJD anyway. Simply fly 1,800 till you get glide slope intercept, follow down to your DA, now you go miss. If you really wanted to know where you are in relationship to Tiki and to Zaza, you use cross radials. Not hard to do, but every time I seem to ask them to do that, they get lost. So we need to train on one particular approach for the multiple ways that you can do it.
Well, on the ILS here, isn't there a feeder route that comes off Treasure View?
There is.
So you could just use that rather than a DME.
The feeder route basically identifies Zaza, and there's another radial right next to it that identifies Tiki. So, but we do the same thing as far as the DME arc. You know, everyone's really good about getting on the arc and doing that. But what happens when we get vectors to that VOR? I can tell you what happens because I went through it yesterday. It ain't pretty. Or if we have to do a full approach, where we fly to the Treasure VOR, outbound, procedure turn inbound. Sometimes on a stage 3 and under course, it's all right, let's do a full approach. Where's that? We got to go to the VOR and then fly outbound, do a procedure turn, go back in. I've never done that before.
You're getting ready to.
So, well, I'm sure you can figure it out. You're trying to be an instrument pilot, but when you train your students, now this is off MEI topic, mind you, but when you train your students, you want to show them everything. Because out there, away from these walls, there's something called America. America doesn't do things like Fort Pierce does it. You know, we have localizers and that have DME that don't have DME. Some of them just have marker beacons. Some of them have to have cross radials. There's a variety of ways of doing things. So, those are the components. Let's talk about how the ILS works, as if we don't already know.
Like that good old 4-course range.
Exactly like that good old 4-course range. Only we're substituting sound waves with radio waves. These will be very high frequency space waves.
Space waves.
Yep. So it's out of this world, this ILS system. So all we do is we tune a frequency, and there's actually two frequencies that are associated with an ILS. We have our localizer frequency and we have our glide slope frequency. Glide slope frequency is sort of, we don't tune that in, it's just kind of paired with the ILS localizer frequency. So when we turn in the localizer frequency, we actually tune in or listen to the frequency the glide slope's transmitting to us on. So the localizer antenna is set back about 1,000 feet, and our little glide slope shack there is on the left-hand side at this airport. Our students can't tell me that for the life of them, but that's where it is, on the left-hand side, little yellow or red and white shack out there. There's typically 750 to 1250 down and 250 to 650 offset the center line. That's where they're going to put it if they wanted to make an ILS. And so that glide slope uses a different frequency, but the same modulation as the localizer. Now when I say modulation, I'm talking about this. That's our 150 hertz modulation and our 90 hertz modulation. When we get too much of the 90 hertz modulation, that kicks our city off to the right, saying, hey dummy, get back to the right. When we get too much of the 150 hertz modulation, it says, hey dummy, go to the left. You're too far to the right. When we get equal amounts, it says, damn, you're good. The glide slope works the same way. Imagine if this was the glide slope and not the localizer. Our 150 is below and our 90 is above. So when the glide slope receiver is getting too much 150s, what are you doing, dummy? Get back up there. It sends the glide slope needle up. Or we're getting too much 90. So where the hell are you going? We have to descend to the airport here. And we're getting the same equal amounts. It's like, damn, you're hot shit. So that's how it works. We use this for guidance to get down through clouds and approaching an airport, and we get our lowest approaches here. Very important when we deal with any instrument approach that we look at the inoperative components table, because if we have inoperative components that may change some things for us, like visibility or altitude, or the visibility only. So this is how the ILS works. We tune it, we identify it, bada boom, bada bing, we follow the needles down. Is there anything else we really need to talk about, like DME, or Doppler?
Talking about radar service and procedures.
Okay. So, let's talk first about radar.
What was DME?
Radar.
You got that?
It's not here.
Here we got a little radar here. Sits at the top of our little radar pole. And we simply spin it around and we send radio energy out and it gets sent back to us. We pick it up and we detect it. Let's see, radio and rain. I forget what radar stands for. Radio and
It's
something detecting.
And ranging.
Radar, radio detection and ranging. There we go. I'll buy that. So, the actual system itself is very simple.
Yeah, that is right.
It gives us azimuth and approximate distance. Azimuth is in the direction from the site we happen to be at, based on that radar energy hitting our aircraft and bouncing back, and approximate distance based on. Now, it only gives approximate distance because altitude, like DME, changes. We're really only getting a slant range. So, this would be a primary radar system right here. And the primary radar system can only display primary returns on a radar scope. Now, by primary radar, I mean that's all you get is a blip on the screen. That's all. It's very hard for ATC to do their thing with just that information. So, after a certain crash in the Grand Canyon, they came up with the radar system, and then it took another crash in the terminal area before we had to have marker beacons. Or not marker beacons, the transponder beacons. So, our aircraft utilizes primary radar, and sometimes we can find a little bar here on top of it, and sometimes it's actually an actual separate antenna that we rotate. We use secondary radar. Secondary radar simply interrogates our transponder. Transponder simply gets a signal and responds to it. The encoder portion of that transponder, which you can find back behind the panel, takes a look at our static pressure, and it tells the secondary radar what our static pressure is. And also, our actual transponder sends the code out with that. So, what we do is we take that static pressure from the static port, and we take our code, and we send that out in a message to our secondary radar, where the secondary radar picks it up and puts it on the radar screen that tells the radar controller what code we're squawking and what our altitude is. Now, the system automatically compensates for the local altimeter setting. So it doesn't matter what we put in our altimeter, it's going to read static pressure anyway. We can put in 31.00 and fly at 7,000. That radar is only going to pick up the static pressure there, and we're not actually at 7,000 because we put in the wrong altimeter setting. So, basically when we talk about radar, we have two different distances. We got within 40 and outside 40. When we're within 40 of the main bang, that's what they call this, the main bang, we get pretty good accurate indications. And as such, when we're in the terminal area, 40 miles, we can expect 3 mile separation. But outside of that 40 mile range, we can expect 5 mile separation. Now we know a little bit of that. Let's talk about what can this give us? What can this do for us? Well, everybody knows about traffic. We can get light following, also called, traffic advisories. As a VFR pilot, they're on a workload permitting basis, and all it requires is for us to simply call up whoever the controlling agency is, tell them where we're at, where we're going, what we want to do. They'll give us a squawk code that we'll put in there, and then they'll follow us on radar and tell us when any aircraft gets close by. For IFR, we use this quite effectively for the instrument system. Matter of fact, IFR would probably not exist without it in today's traffic volumes. So, there's other things we can do with this radar as well. When we put a radar at the airport and we turn it down the runway, we can use it for approach. When we look at the radar approach minimum pound in the TPP, it's based off a radar system that literally is looking down the runway at you. You can get precision approach radar, which gives you azimuth and altitude, or just ASR, airport surveillance radar, which gives you azimuth only. And now through instructions given to you over the radio, you can fly this airplane down to make an approach on that runway. So for VFR guys, hey, we use this for flight following or when we're lost. Lost procedure is very important. If we don't know what we're doing, we have to climb, confess, and start talking to them. Hey, I'm lost, student pilot, or I'm a brand new private pilot, I don't know where I'm at. They can have a squawka code and ident and tell us exactly where we're at, and then tell us, hey, you need to go this direction to get to the airport you're going to. So it's very helpful. Any questions on that?
Nah.
We all dealt with radar before.